the search runtime complexity of an element of order of 1 time. Okay, so let's look at some definition. When you talk about direct addressing, it is when you have, but before that, we assume that if you want to use the direct addressing, you need to make sure that your universe of keys, okay, is reasonably small. Okay, because basically you want to prepare the array for all of the possible key in your universe. And then suppose that you have an application that needs a dynamic set in each element, which has a key drawn from the universe. So basically, your universe will contain a 0 up to m minus 1 element. And again, as I mentioned, since we want to make sure that our key needs to be reasonably small, so m should not be too large. So m is the table size, okay, or the array size, okay. And then we assume that there are no two elements of the same key. All right, so let's say, for example, if we look at this direct address table, so let's say, for example, we have this universe of keys, okay. So here we have some integer 9, 0, 6, 2, 3, 5, 8. Okay, and then out of this universe, these are the actual keys that you use in your data or in your implementation. So a direct address table is when you will create a table of size 0 up until m minus 1, okay, and then you will map the keys into the array. Okay, it's just like I think this is something similar like when you do the counting sort, where you sort of like put the element inside the respected array, right? So this is something almost similar. Okay, so but then this is not like we are not doing counting here. It's just that we want to keep this element in the array corresponding to the index. So let's say, for example, you have key 2. This will be kept inside index 2. All right. And let's say you have key 3, and and you will keep it inside index 3. Okay. So if you see here, in order for us to do the search, all you have to do is just we return the array in the array of the element inside the array of tk. Okay, so this one we can say that the runtime complexity for this one is order of 1, right? Same goes for insert. It is just like we get the key and we just insert the key into the array with the same index. Same goes for delete. You will just delete whatever key inside the same index. Okay, so each of these operation will take order of 1 time. All right. So yeah, so basically this is how you do the direct address table. But do you see a problem when we do direct address table as such, class? Do you see any problem if we want to implement a hash table, a direct address table for this one? Do you see any problem? We have the running time complexity of order of a constant operation. Do you see any problem with this one?
Some
Class?
keys does not have value.
Yeah, so basically you are wasting your array, right?
Yes, yeah.
So basically, so in a sense, if we apply this technique, open direct addressing, one of the major drawback is that we have a lot. If like let's say, like in this case, this is our universe, and let's say that this is the only actual key that you use within the element, so you are wasting spaces. Okay, so you're wasting your space. So in the sense that would be so like, let's say for example you know, like suddenly out of the actual keys, and then you have let's say the range of the key is 50, and what all you have to and the only thing that you use is just like 5 or 10 numbers. So basically you're wasting your table. So one of the major drawback of direct addressing is the space. Okay, even though you can get the search, insert and delete in order of one. Okay, constant time. Okay, so just as a comparison, if we look at so normally when we do search, when we do a linear search, just for a comparison, you know, like the reason why we are actually trying to get you know, like our search into constant. So we talk about the linear search. What is the running time complexity for searching for a linear search class? It will be order of n, right? And then let's
Yeah.
say, for example, we have looked into binary search. So binary search is better. So binary search, what is the running time complexity for binary search? It is, remember, you know, like when we have a sorted array, and then you know, binary search, we look, since if like let's say we are looking for the key, we find the middle element, and if it is bigger, if the key element is bigger, we only have to look into the upper subarray and eliminate the lower subarray, and we do this the same thing again, and we keep eliminating half of the array. So what is the running time complexity for searching in using the binary search? It will be order of order of
Log n.
order of log n, right? So today, by using the so basically hash table will perform even better, whereby we are trying to use so basically when we use hash table, so we want to get our search into order of one. So it's more or less a constant. We're not in a sense, it is not going, so if um uh, there's a possibility that your hash function the worst case running time will be order of n. But as I mentioned, if you implement it properly, so it is generically you can say that the search using hash table, the implementation of using hash table is constant. Okay, order of one. Okay, so this is the so we looked into the direct address table, and we see that the major drawback is that the waste of space. So therefore, we need to do something about this. All right. So as we see here, the downside is, if like let's say the universe is large, maybe impractical, even impossible given the memory available on a typical computer. Okay. And then maybe that the actual keys that are actually stored may be small relative to the universe of keys, and the table would be wasted. So what we're going to do is we are going to improve this with hashing. Okay, so we're going to put some kind of like a mathematical equation in between, so that we can make it better. Okay, because we know that if we use the direct addressing, we can actually we can almost get we can get the order of one running time. Uh, but we're going to make it, we're going to improve it a little bit by implementing the hash function, and basically use the hash function to calculate what are the slot for the keys from the key k. Okay. All right. So let's look at this figure. Okay. Which shows how hash function hash function is used to map the keys to the hash table. Okay. So basically, when you use the hash function, it is actually reducing the range of the array indices, and therefore reduce the size of the array that you need to use to keep the keys that you use in your universe. Okay, so it doesn't matter how big is your universe. So all you have to take into consideration is the size of the table, and the keys that you want to put inside the table. Okay. So yeah, so as I mentioned, instead of size u, you can have some table of size m. Okay, and then you will have a hash function h that maps the keys to the hash table. Okay, between 0 to m minus 1. And then so the size of the table is normally is smaller than the universe. And then you will have the hash function that maps the key into the slot. Okay, so let's say, for example, we have this universe of keys, and these are the actual keys that we use. And then we have some hash function that we define, hash k, to map the key into the slot. Okay, so let's say, for example, this key, after we apply the hash function, this key will be mapped to this slot. For this one, if we apply the hash function, this key will be mapped into this slot, and so on and so forth. Okay, so but then there's a possibility that your hash function is going to create a collision. Okay, so if let's say, for example, here we look at these two keys, K5 and K2, whereby after you apply the hash function into K5, it maps into this slot. When you hash this key as well, it is also mapped into the same slot. So remember, when you do the wrapping cup, there's a possibility that you get the spurious heat, because like some of the windows will have the same hash value. So this is what it meant by collision. Okay, so you have two different keys, but when you apply the hash function, it creates the same value and it will map into the same slot. Okay, so this is what we call a collision. So for the hash table, there are two ways of how we can resolve the collision. One is we use the chaining method, and the other one is open addressing. Okay, so let's look at the first method on how we can resolve collision, which is the chaining. Okay, so for using chaining, okay, to resolve the collision, what we do is that whenever we have a key that hash into the same slot, we create some kind of linked list, okay, outside of the table. So in a sense, inside here, there will be a pointer pointing to a linked list. Okay, so whenever there's a collision occurs, you will append the new element at the end of the linked list. Okay, so for example, here we have these two elements, okay, hashed into the same slot. So first, K1 is we apply the hash function. It is applied here in this slot, but instead we keep inside the array. We create a linked list. Okay, so basically the array will keep the address, will keep the pointer pointing to the linked list. So K1 will be inside this list. Okay, and then let's say, for example, you hash key K4, and it hashed to the same slot as well. Instead of putting it inside here, we add to the end of the linked list. So basically, whenever there's a collision occur, you will just append it at the tail of the linked list, okay, at the end of the linked list. All right. So this is one of the way of how we can manage collision in the hash table. So for the running time complexity for the hash insert would be order of 1. For the hash delete, is also order of 1. Okay, so basically we just apply the hash function, and we try to look at the slot, and then we delete the key. And no, I think for this one we still need to do some search right before we delete. But basically the delete would be order of 1, because all we have to do is just find the key, and then we delete. We just take away the element from the list. Okay, but how about the search class? How about the search? What is the running time for hash search in this case using chaining? Can you say something about what is the running time complexity of the search if we use chaining to manage our collision?
It's the length of the linked list of the given k value.
Okay, so basically the possibilities of you doing the search, it will be the length of the linked list. Okay, so what happened if, like, let's say for example your hash function is very bad? What is the worst case running time complexity for this one? Class? What is the running time complexity? The worst case running time complexity for this implementation? Can you think of, what is the worst that can happen for this implementation?
The chain comes too long.
Sorry?
You were asking like the consequence of chaining, right?
The what? Sorry? The
consequences of chaining.
Yeah, basically, not the consequences of chaining, but what is the worst case running time for this strategy? What is the worst that can happen if you want to apply this strategy?
Is it O of n?
It'll be order of
averages
n.
into one slot.
Yeah. So basically, the worst thing that could happen is that when you have all your keys mapped into the same slot, and therefore the search would be order of n, which is the length of the linked list. Okay. All right. Good. Okay. But then there are advantages of chaining, which is, like normally for this strategy, they are very easy to implement. Okay, because all you have to do is just that whenever you have a collision, you just append it to the end of the linked list. And then one of the thing is that your hash table will never be full, because you can always add more element to the chain. But then there's a how do you call that? There's a trade-off a little bit, like even though, like we know that our hash table is not going to be full, but as the size of the chain grows, it will somehow affect the running time complexity for the search. Okay, and then we're going to be discussing this a little bit later. And then it does not depend much on the hash function, so it doesn't matter, like you can just use any hash function as long as it is mapped into a slot and you keep it within the list. But then again, as I mentioned, like we need to somehow take into consideration about that worst case. We do not want most of the key slot into the same, being mapped into the same slot. And then normally we use this scheme when when basically the number of the key to be inserted or deleted is unknown. Okay, so these are some of the reason or advantages of using chaining. Okay. The disadvantages of chaining, you still have that wastage of space. Okay, because basically your hash function does not really, like the mapping of the keys to the slot does not really depend on the hash function. Okay, so if let's say for example, like even though there's a collision, you somehow create an external list to keep whatever keys that is being mapped into the same slot. Okay, and then just now as we discussed, if let's say the chain becomes long, the search time may become order of n in worst case, and then we need extra memory to keep the link of the addresses. Okay, so if you imagine like if like let's say the chain becomes long, it may moving towards the order of n running time complexity, okay, of using hash table. Okay, so a little bit analysis on hashing with chaining. Okay, so as I mentioned just now, the running time complexity for implementing hash table with chaining is that if like, let's say for example you keep, even though that you don't it doesn't really matter how big is your what are your hash function as well as the table, but then like if like let's say you have let's say if you have a number of elements slot mapped into the same slot, and it will go up until order of n running time complexity. Okay, so in order for us to make sure that that does not occur, we need to try to make sure that our load factor alpha here, our load factor alpha is less than 1. Okay, so basically a load factor alpha we can define as load factor alpha, we can define it as n over m, where n is the number of keys and m is the size of the table. Okay, so these are the load factor alpha. But for in this case, the best way is I mean for chaining, basically we want to make for hashing, normally we want to make sure that the load factor alpha is lesser than 1, but it can be greater than 1, because since when you use chaining, so you can have a table size that is smaller than the size of the linked list. Okay, so for chaining, there's a possibility that the load factor alpha is greater than 1. Okay, so basically like we want to make sure that when we want to do the hashing with chaining, we want to make sure that we try to have the load factor alpha less than 1. Okay, because this load factor alpha, if the load factor alpha is equals to 0, meaning that the table is empty. But if like let's say the load factor alpha is 1, not really like for chaining it doesn't really apply anything, but then later on when we use the open addressing, when we say that when our load factor alpha is 1, we can say that our table is actually full, and we need to do some rehash. We need to extend the size of our table and rehash all the keys. Okay. All right. So that is about the load factor alpha. Any question so far for this one, class?
Since in that it says it can also be greater than, so it's greater than like overload.
It's not overload, but then basically the hash table basically the hash table, the performance will start to decrease. Okay, because you want to make sure that we want to make sure that when we do our search, the running time complexity is constant. So if like let's say our load factor alpha, if we use chaining, is starting to grow bigger than 1, so meaning that there are some slot that will have a long basically the distribution of element when you do the hash map is not uniform. Okay, it's not balanced. So that meaning in a sense, there are some element that is one or empty, and so on and so forth, and you have that one slot that have a long chain. Okay, so basically, that's why when we talk about the hashing with chaining, we need to make sure like our load factor alpha is like not like too big. We don't want it to be more than one. Okay, so that we have that running time complexity in constant time. Okay, for doing the search, delete, and insert. All right. Okay. Anything else regarding this class? All right. All good. Smaller alpha means better. Not really. Smaller alpha means that the table is not. It's just that the table is not full. The table is not full, and we know that our running time complexity will still be around how do you call that, around constant. Okay, so basically when you do the search, for, let's say, for example, the running time complexity for search would still be order of 1 plus some what are the value of the load alpha. Basically, what are the extra things that you need to do, like the extra search for the linked list. Okay,
So is it
So
like we
then-
want the value be as close to 1 as possible, but not necessarily land on 1?
I in general, I think as long as the load factor alpha is between 0 to 1, we can safely say that our distribution of the mapping using your hash function is uniformly distributed, and you can get the running time complexity of order of 1. With that, yeah.
Mm.
Okay. All right. So so I guess we discussed this. Basically, the average case performance of hashing, depending on how the hash function distribute the set of key among the M slots. Okay, on average. So we want to make sure that the running time complexity for insert, search, and delete is order of 1 plus alpha. Okay, and then the worst case behavior is the one that we do not want. Basically, is when we have all the key hash into the same slot, which create a list of length n. All right, and then therefore the random complexity can go up until order of n. All right. So in a sense, it is no better than we use a linked list for our elements. Okay, so for our key. So in a sense, for this strategy, okay, we have to we assume, or we try to make sure that all our keys or the given element is equally likely to hash into any of the M slot independently. Okay, where any other element basically we call this as a simple uniform hashing. Remember when we talk about probability, and we have that when we talk about the randomization, and we want to make sure that the probability is equally likely. So same goes for when we do the hashing. The hash function, we need to make sure that they are going to hash your key equally likely into all the M size slot. Okay, so so that we can make sure that we can keep the load factor alpha small, and still have the runtime complexity near to constant. Okay. But then for chaining, I think it is okay, still okay. If the load factor alpha is more than 1. It's just that we need to make sure that the chain does not get bigger than the size of the table. You get what I mean? The element may be bigger, it's just that we do not want it to get, run into order of n time. We just need to make sure that the length of the linked list does not exceed the length of the table. Okay, so else then the running time complexity for the search may go up until order of n. Is that okay, class? Only for chaining.
Okay.
Okay. All right. So since now we know that the hash function is very important, okay, basically it is the one that will determine how your keys are going to be mapped into the slot. Even though chaining, the hash function does not really it is just being used to map, and then it doesn't matter, like whether you do not have to do a second hash function in order for you to find a slot, because it is being kept in a separate list outside of the table. But then you need to make sure that your hash function is able to do the simple uniform hashing, okay, whereby each key is equally likely to hash into any of the M slots. All right. So in this case, there are two methods of how you can write your hash functions. One is the division method, and the other one is the multiplication methods. Okay. All right. So before that, we need to understand or somehow set some assumption. Most of our hash function assume that our universe of keys will be a set of natural numbers. Okay, so if let's say your keys are not natural numbers, you need to find a way to interpret them as natural numbers. So again, when we look into how we do the rubbing cup, we try to use the ASCII value of the character, and then we hash those value in order for us to find the hash value for that window of characters. Okay, this is what you mean by that. We assume that hash function will assume that the keys are natural numbers. Okay. Or maybe if let's say you have a character string expressed as an integer using some suitable radix notation. Okay. So the rest of this lecture, we will just assume that our keys are all natural numbers, right? Okay, so let's look at the first method, okay, in creating the hash function, which is the division method. So this is a simple one, okay, a simple method whereby how you map the key, okay, you map the key into M. All you need to do is doing the division, or is finding the remainder of K divided by M, which is M. M is actually the size. M is size of table. Okay. K is the value of key, and M is the size of the table. So for example, if you have a table of size 12 and you have a key 100, okay, to be kept, okay, to be put inside your hash table. Therefore, when you apply the hash function, you're gonna get 4. So basically, if let's say you have 12, 0 up until 11 array, okay. So 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, and we want to so if let's say our key is 100, our M is 12, our hash function is K modulus M, and if let's say we have our key is 100. So basically, we're gonna get, so when we hash 100, we're going to get 4. Okay. 100 modulus 12. Okay, and then we're going to get 4. Sorry, we're going to get 4. Therefore, 100 will be in this slot. Okay, will be mapped into index 4. That is what it means by the division method. Okay, the hash function using the division method. Okay, so there are some consideration, okay, in order for us to make sure that our hash function is okay. I mean not going to give you the worst case running time complexity. We need to consider our m value, and it should not be a power of 2. Okay, since if we have m to some power 2 to the power of p, then basically your hash function is just going to be the lower order bits of k. So basically it will cause you a lot of problem when you do the hash. So there's a possibility of a lot of collision and so on and so forth. Okay, and then you choose the size of the table as a prime number. Okay, not too close to the exact power of 2. And normally that will be a good choice of your table size. Okay, so therefore again, remember when you do the wrapping cup, you choose the prime number. Okay, that is used for your hash function, and we want to make sure that we use a prime number that is not too close of the exact power of 2. Okay, and then therefore we can reduce somehow the number of collision when we do the hashing. All right, so this is the division method. So the multiplication method, there are several steps that you need to do. Okay, first you have to, in multiplication method, in step 1, you have to multiply the key with some constant value a. Okay, so you need to define the constant value a as 0, in between 0 to 1. And if you look at the Knuth's suggestion, you can use this value for the constant. Okay, the constant value. So if you remember the algorithm book that I show you, it's written by Knuth. So that book suggests that so basically Knuth suggests that the constant value that we can multiply the key with is 0.618033988. So that's the reason behind it. I haven't really go through how Knuth find out about this value, but you can always if you're interested, you can always look for read it later. Okay, so basically Knuth suggests we use this value for our constant, okay, and multiply it with key. After that, we extract the fractional part of Ka, okay, and in that case, we're going to get another number between 0 and 1. And in the third step, you multiply the fractional part with the size of your table and take the floor value. And by doing this, you're going to get some number between 0 to m minus 1. And this will be the slot for your the slot for the key in the hash table. Okay, so therefore, basically, you can apply this function. Okay, hash k floor m times ka mod 1. Okay, or you can also have or you apply the hash function floor m times the fractional of ka, and basically the fraction. How do you calculate the fraction of x is x minus floor of x. Okay, so the way of this method, the multiplication method, as a hash function, it requires some kind of calculation first. So a little bit of extra calculation in order for you to find what is the value for the slot to be mapped for the key, right? All right, so those are the two methods that you can use for for hash function. Okay. All right. Next, we are going to see how are we going to resolve collision using open addressing. Okay, so before that, open addressing, the difference between, like having a hash function that do hashing in hash table chaining is that in the one that we see just now, the one that we do hash table chaining, we keep our element outside of the hash table itself, and the hash table only keep the address that points to the list. Okay, so basically the element is being stored outside of the list. In open addressing, the hash value will be kept inside the table itself. Okay, so that is the difference between the one that hashing with chaining and open addressing. So in open addressing, we need to so basically there are ways we need to resolve the collision for open addressing, because like let's say but because if you imagine for if like they say we're using the chaining strategy, it is quite trivial, like if there's a collision, all you have to do is just add towards the end of the linked list. But if like let's say you want to keep the element only inside the table, we need to figure out how, if like let's say we have K1 and K2 being mapped into the same slot, and we need to find out how are we going to handle this problem. Okay, by like by still keeping all elements inside the table. So basically in open addressing, element will occupy the hash table itself, which means that each table entry will contain either an element or nil. Okay, we need to set it to nil. Later on, you're going to see the reason why we need this is very important, because of how we want to determine how the keys are going to be inserted into the table. Okay. And then when searching for an element, we are going to systematically examine the table slot until we find the key, or that we can make sure that we can be assured that the element is not in the table. Okay. And as I mentioned, for open addressing, there's no element stored outside of the table. And therefore, if we are using the open addressing, our table can be filled up. Okay, and therefore no insertion can be made, and therefore the load factor for open addressing can never exceed 1. Okay, remember when we talk about the load factor alpha, if we say the load factor alpha is 0, meaning the table is empty. If load factor alpha is 1, meaning the table is full. But for hash table chaining, it doesn't really matter, because basically the table is not going to be full, because the element is going to be stored outside of the table. Okay. All right. So that is open addressing. So in order for us to resolve the collision using open addressing, we are going to do some probing. Okay. So basically, when there is a collision, you need to do some probing inside the hash table to find what are the next possible empty slot for you to put in the key. Okay. So okay, so instead of being fixed, so if like let's say for example in chaining, the search may require up until order of n search time. So if like so if you're using the probe, if you're doing the probing, the position of the probe will depend on where is the key is being inserted. So later on, you're going to see how far in the hash table that you're going to search until you encounter either the deleted or the nil array. Element inside the hash table. Okay. All right. So basically, to determine which slot to probe, we are going to extend our hash function to include a probe number. All right, as a second input. So let's say, for example, you have this hash of 0 up until n-1. You're going to have an additional hash function that will do the probing. Okay, so basically, we're going to have a probe sequence where you're going to have, let's say, for example, if the first probe there's a collision, you need to do the second probe, which is hk of 1, and so on and so forth until hkm-1. Okay, so basically there's a sequence for your probing. And it needs to be a permutation of the size of the table, okay, 0 up until n-1, so that every hash table position is considered as a slot for any new key as the tables fills up. Okay, so so next we're going to see what does it mean by that. You will see that whenever we do probing, we are going to try our best to fill up, okay, the table, right? Okay, let's look at how is the open addressing hash insert and search is going to be done. Okay, so as we said just now, for open addressing, the slot may either be a key or nil. Okay, if the slot is empty. For the hash insert, here, if we look at the pseudocode, what we're going to do is that we're going to take input as hash table T and a key K. So basically, it's either returning the slot number where it stores key K, or it flags an error because the hash table is already full. Okay. And for the procedure hash search, it takes a hash table as the input and a key, and then will return the value if key K is found, or nil if the key is not present in the table. Okay, so these are the two pseudocode that for open addressing. Okay. All right. All right, for open addressing, the hash delete is a little bit complicated, okay? Because if, like, let's say, for example, we apply hash table with chaining, all you have to do is just we manipulate the linked list that we have for that slot, right? So the delete would be just of you reassigning the pointer of the linked list. But for open addressing, the deletion is a little bit complex, okay? Because when you want to delete a key from slot I, we cannot just simply make mark that slot empty by storing nil, okay? Else, because if we did it, we might not be able to retrieve any key K during insertion. You know, like when you want to do your probing, and basically when you want to do the insertion and you probe that slot, and you may found it occupied. Okay, so that's why you cannot put a nil inside it. Therefore, to solve this problem, instead of marking the word marking it as nil, we are going to mark it as deleted. Okay. And then basically we are going to modify a little bit the hash insert to treat that if, let's say, for example, that slot is deleted, we can actually insert new key there. The reason for this is that, you know, like when you delete a key later on, when you want to probe, when you want to search the key, if we put it as nil, it means that some of meaning the search for the key will be stopped there, will stop there instead of continuing further down the table. Okay, so later on we're going to see what do I mean by this. All right, so that's why we're going to put it as deleted instead of nil, so that, you know, like when you do the search, it can complete the search until the end of the probe. Okay, the probe sequence. Okay, so for that probing technique, there are three ways you can do the probing. One is the linear probing, quadratic probing, and the double hashing. Okay. So we have around 8 more slides. You want to continue and finish this? I always say finish early, but you know, we always used up all the 2 hours without break. So do you want a break or do you want to continue, class?
Short break.
A short break. Okay. So before we go for probing techniques, maybe we can have a short break, like 5-minute breaks. Is that alright, guys? Okay. So I will see you at 4:05. All right. Okay. So so let's continue our lecture. All right. So up until now, before our break, what we did was we have looked at hashing with chaining, as well as how and hashing we using open addressing. And then we know for chaining is a way of result. One of the way of resolving a collision is by using the chaining, and the element that you want to keep is being kept outside of the table. While in open addressing, the key is going to be kept inside the table itself. And how are we going to solve the collision is by doing probing, okay, to see what are the next available slot for the key to be inserted. And there are three techniques of doing the probing in open addressing. And they are linear probing, quadratic probing, and double hashing. So we're going to look at each of these techniques next. Okay. All right. So first, let's look at linear probing. Linear probing. Okay. So linear probing is a straightforward probing. Okay, whereby when like let's say for example, okay, you have a key hash into the same slot. Okay, so if like let's say this is being occupied, this is being occupied, this is being occupied, and then let's say for example another key is being hashed into this slot. Let's say for example, so in order for finding the next slot in linear probing is that we're going to be looking at the next slot whether it is empty or not. So if in this case the slot is not empty, we're going to put K inside this slot. Okay, so like let's say for example there's another key X that is coming in, and it is mapped into this slot. It's hashed into that slot. Linear probing, you will just try to keep looking for the next empty slot. So therefore, in this case, the next when this one when it goes into this one, it is not empty. Okay, because there's an element there. You will continue looking for an empty slot, and therefore, since this one is empty, X is going to be slot into this slot. Okay, so linear probing, basically the concept is very easy, which is all you have to do is just find what is the next available slot for the key to be inserted in the hash table. Okay, so basically how do you do that? It's like if we define it mathematically, it's like apart from the hash function that you have, there is also an auxiliary hash function that somehow that you need to do, whereby the next hash function is like you're going to apply the same hash function but plus one. Okay, so you're going to keep increasing the value plus one. Okay, so for example, let's say for example we have these keys and we have our table size 10, right? So in linear probing, so let's say, so basically for, if like, let's say we use the division method. Do you remember how we write our hash function for division method? It would be hash k. What is the hash function that we can use? Division method? It would be k mod m, right? Okay, so if let's say we have k mod m, right? K mod m. So now we're going to start hashing our key into our hash table, right? So our first key is hash 89 and 89 mod 10, we get 9, right? So we are going to slot 89 into slot 9. So our 89 is going to be here. All right. We go to the next one. The next key is H18. So H18, we're going to get 18 modulus 10, and we're going to get 8. And we're going to put 18 inside slot 8. Next one, we're going to hash 49. Let's say, for example, we have key 49. So 49 mod 10, we're going to get 9. But in 9, there's a collision, right? Because here in slot 9, we already have 89. So how are we going to find the next slot? Is that so for the next one? So we can say that normally I like to write it hash 0 of 49. It would be 9 plus 1, and we're going to mod m. So what are we going to get? We are going to get 0. Or basically, what you have to do is that we are going to look for the next available slot, which is in slot 0. So we can put 49 here. Okay. So the next key is 58. So H58. So 58 modulus 10, we're gonna get 8. So therefore there's a collision, right? Because we have 18 inside slot 8. So we're gonna have collision here. So if we calculate the next sequence, so if we have H0 of 58, we're gonna get 8 plus 1 mod 10, which is 9 mod 10, we're gonna get 9. But in this case, our 9 is still occupied. So we're gonna do the next sequence of probing, which is H1 of 58. We're gonna say that 9 plus 1 mod 10. So 9 plus 1 mod 10 is also is 0. Also there's a collision, okay, because 49 is already occupying slot 0. And we're going to continue our probing sequence. So we call it is H2 of 58. So 0 plus 1 mod 10, and we're going to get 1. So therefore, we're going to put 58 inside this slot, okay? And the last one is 65. So we have 65 is 65 mod 10, and we're going to get 5. So 5 is empty, so we can put 65 in slot 5. Okay, so just now here, for 58 here just now, what happened is that for the first hash, we got 8 and there's a collision. What we actually was doing was we are actually looking at whether the next one is empty. So in this case, this one is not empty. The next one is not empty. And the next one is empty, and therefore we put 58 inside slot 1. Okay, so this is how you do the linear probing. Are you good so far for this hash function? For this hashing using linear probing? Yeah. It's
Yes,
pretty
yes, yes.
straightforward. Okay. All right. So, but there's some disadvantages actually. Even though the implementation is pretty straightforward, like it's very easy. All you have to do is just go look for the next available slot. Okay. But it is easy, okay, for linear probing to suffer what we call as the primary clustering, okay? And therefore, if like, let's say, for example, if like, let's say, so basically, in a sense, if like, let's say, the hash function keep hashing into the same slot, and basically all you have to do is just like you are trying to fill up some portion of your there will be some clustering in some portion of the array, okay? And okay, so wait, let me finish this one first. So if like, let's say, for example, okay, so if you look here, okay, what does it mean by primary clustering is that if like, let's say, for example, another element that is going to be added that is going to be mapped into this slot, you will keep having a longer probing sequence. So in a sense, when you need to find that key, you will have to search it more inside the hash table. So basically, the probe sequence, the longer the probe sequence, the longer would be the time that you need to search for the key, right? So therefore, for linear probing, one of the problem is that you're gonna have you may get that primary clustering, okay? And then it will get even worse, okay? If the occupied slot, if most of the slots are being occupied, okay? When you search for the key, it will take longer. Okay, so imagine okay, so if like let's say, for example, you want to go and search for 58. Okay, so let's say, for example, we want to go and search for key 58. So we do the hashing again. So we're gonna get 8, and we know that we are using linear probing. We are going to keep moving, keep looking at the next slot. Okay, this one, is it 58? No. We go to the next slot, is it 58? No. And then go to the next slot, is it 58? No. Yes. Okay, so we find the 58 in slot 1. So if let's say we have another element, say 48. So we can say that it is going to be mapped into slot 8 as well, right? For if like, let's say, for example, we have 48, let's say 48, we're gonna map into the same slot. We're gonna do linear probing, and basically 48 is probably gonna be there. Imagine if we get like another let's say, for example, 28. Let's say, for example, 28 is probably going to be here. So do you see that there's a possibility of having that primary clustering? And in order for you to find that 28, you need to find it sequentially until you encounter the nil. Okay, so all this empty slot is already being specified as nil. So once you encounter the nil, then the search will stop. And therefore, like, let's say, for example, you try to find 68, let's say, for example, and it is not in the table because let's say, for example, you hash that 68 into slot 8, and then you keep probing until you encounter a nil. Therefore, you can say that 68 is not in the table. Okay, so that's why it is important for you to define the empty slot as nil, because it will how do you call that? It would make your when you want to search for the element, it will make it stop. It will stop the probing sequence. But here, if let's say your table is starting to fill up, okay, in linear probing. Let's say, for example, this one we're gonna, instead of nil, we're gonna say there's another one here, 68, let's say, for example. So imagine, you know, like if you want to find something like 78, your probing would be starting from here, going down here, going up, down, 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 down. And since there is no nil, you're going to keep looking until you find this nil. Okay, so imagine if your table is starting to fill up. Let's say, for example, here, we say that, for example, we have another one, say 55 here. Imagine, in order for you to find that is it 78 just now? You probably need to probe until you find this nil. Okay, so therefore, when you do the linear probing, that would be a problem. Okay, when you want to do the search, one, it will create this primary clustering, as well as it will increase the average search time because you cannot find the empty slot. Okay. All right. So again, I also wants to show you the reason why we need to say delete instead of nil. Okay. So let's say for example this is nil, and let's say for example you run a function delete for 48. Let's say for example, so we delete 48. Okay. We want to let's say for example we delete 48. And we want to search for 28, let's say for example. Okay, so the reason why we need to put delete instead of nil is so that if, like, let's say for example we want to search for the key 28 after we delete the 48, okay, we want to make sure that our probe continues on even though that this slot is empty. Okay, because this is delete, we want it to keep probing down until it encounter the nil. All right. So therefore, we want to make sure that we found that 28 key. Okay, after the delete. So imagine if we put nil instead of delete here, your probing is going to stop here, and you're going to return that 28 is not in the table. Okay, so therefore, that is why when you do the delete, you need to put the delete so that when you do the probing, the sequence will continue until the end. All right. Are you good so far, class? That would be the linear probing. All right. Okay. So suppose if we have n values in the array with all values as 58, then it will hash n minus 1 time. I don't get what you mean by that. N values in the array.
I think what he means is like, say there's an array with like 10 elements and all 10 elements are like 58. And then we want to store them in like a hash. We want to store them as hash. So then since all numbers are the same, then all would end up at would have the same starting point. So it would to hash like n minus 1 times. Like it one is full and then the next one, then the third element we have to go through the same process but with one more depth.
N minus 1 time. Sort of value. Meaning in a sense that keys mapped into the same slot. Is that what you mean? I still don't understand. Are you saying that so what is it what you're trying to say is that, like what I said just now, if like let's say for example all the values, like say for example the first hash is hashed into the same slot, and then it will keep increasing, so it will hash n minus 1 times. You mean the kind of like I'm not sure why you wanna ask that. Then yeah, so basically it will hash not n minus 1. Yeah, it basically the probe sequence, not the hash. The probe sequence. The probe sequence will be n minus 1, if you're that is what you're trying to say, like with all the values being hashed to the same slot, if that is what you mean. Okay, do you get it, Kamal? It's not the hash running n minus 1 time, but the probe sequence. Yeah. Okay, so what if the data index is replaced with another element? For example, we're adding 22. How can we find? You can still find 28, because when you do the probing, all you need, all you're checking is that we are checking whether the slot is occupied or not. Junwei? So if like let's say let's say here is 22, if like let's say here is 22, if you want to find 28, you can still do it, because you are looking at whether the slot is occupied or not, and not the value. That's why if like let's say for example the table is almost full, let's say for example this one is also with some number, let's say 11. So imagine, like if like let's say that key is the key when you want to search the key is hash into 8, and the probing sequence will get longer because it does not encounter the nil. So the nil act as a stopping point for the probing. Yeah. Okay, so for when you do the probing, that will be the point where you stop probing. All right. All right. Okay, so let's look at the next one. Okay, the quadratic probing. Okay, so for quadratic probing, it is just like the linear probing. It's just that and since we know that for the linear probing, there's a possibility that we get that primary clustering, which is not good. It will increase the average search time in the hash table. We can apply what we call this quadratic probing to make the clustering a little bit less critical. Okay, you may get a clustering which is called the secondary clustering, but secondary clustering is is less severe than the primary clustering. Okay, so how do we do the quadratic probing? Is that instead of we add +1 each time we do the probing sequence, so we +1, we +2, +3. In quadratic probing, what we do is that for each sequence, we plus with 1 squared, 2 squared, 3 squared, and so on and so forth. So that is the only difference between the linear probing and the quadratic probing. Okay, so let's try and look at an example again. So in this case, our HK is equals to K mod 10, right? Since our M is 10. So let's look at the first one. So H89. So basically we get 89 mod 10. We're going to get 9. So we hash 89 here. So next is hash key 18. So 18 mod 10, we're going to get 8. So we're going to add 18 here. So 49. So 49 mod 10, we're going to get 9. And there is a collision, right? So for the next hash, instead of the +1, we're going to plus the I squared. Okay, so basically for the hash 1, so we are going to say that so this one just now, what did I do? Oh, so I think it's easier if we put it as 1, 2, 3, so that we know what is our sequence. Same goes for this one. So H149 is equals to 9 plus 1 squared mod 10. So what are we going to get? So 9 plus 1 is 10, mode 10, and we're going to get 0. So we can put 49 here in this slot. Okay. The next one is 58. So hash 58. So 58 modulus 10, we're gonna get 8. So that's a collision. And we're gonna start doing the second hash function. So the first probing, 58 is equals to 8 plus 1 squared modulus 10. What we're going to get? So 9 mod 10, we're going to get 9. So 9 is also occupied, so there is a collision. We're going to do the second probing. The second, we are going to continue probing the next slot, which is the second probing of 58. So 58 is equals to 9 plus 2 to the power of 2 modulus 10, which is 9 plus 4. So 9 plus 4 mod 10, we're going to get 3, right? So therefore, we're going to put 58 in slot 3. Are you good so far? Are you good? Right?
Yes.
So instead of adding, like, instead of adding, this is just adding the square of the number. Okay.
Yeah, it's just like linear probing but then instead of we plus 1, we square it. Okay, and therefore that is why they call it the quadratic probing. Okay. So so basically you have the last one, H65. So 65 mod 10, we're gonna get 5, and 65 is going to be here. So do you see, we sort of like already eliminate the primary clustering. So imagine if we how do you call that, we mode this thing into here. So basically you're not going to get that primary clustering. Okay, so because the jump is being handled in quadratic, so the jump is quadratic, okay, for finding the next slot. Okay, so that is for the quadratic probing. The last one, the last technique for doing the probing is the double hashing. This one is a little bit different because you will have two different hash function that will be used to find to do the probing. Okay. So one of the good thing about double hashing is that it eliminates totally the clustering. Okay, because in a sense you are not going to get any clustering. Okay, because the second hash function does not depend on whatever value that you have previously. You are going to have a second different hash function that you create for finding the next probing sequence. Okay. All right. So basically, when you do the double hashing, basically the permutation will have many of the characteristic of randomly chosen permutation. Okay. And in double hashing, what you do is that for the next probe, you have one hash function and plus with the second hash function that you're going to define. Okay. And for the second hash function, it is not okay. So bear in mind, this is the difference between those linear probing, quadratic probing, and in double hashing, the second hash function, the value that you get after you do the second hashing, is instead of the value that you use to that will indicate which slot that the key is going to be put in, it will indicate how many jump that you need to do for you to put in the value. Okay, so let me show you an example. Okay, so so as usual, we have the same case here: 89, 18, 49, 58, 65. Okay, and we have the first hash function, the normal one, which is the division k mod m, and we define the second hash function as hk 7 minus k mod 7. So basically, this value, normally this value, we try to find like a primary value, primary number value that is lesser than the table size of your m. Okay, so in this case, I choose 7. You may find a different hash, a second hash function. If let's say you look at a different example, you may find that some other example will use a different second hash. Okay, when you do the hash function using the double hashing. So so in this example, I'm going to be using this hash, okay, function for my second hash, right? So let's try and do this. So so we got H89, so 89 mod 10, we got 9. So 89, so we got 18, 18 mod 10, we got 8, so 18. So H49, 49 mod 10, we got 9. So this is where you will get collision. Okay, so when there's a collision, different from what we did just now with the linear probing and the quadratic probing, we are going to apply the second hash function. And in this case, we are going to do the second hash, H2 of 49, which is 7 minus 49 modulus 7. So 49 modulus 7, what do we get? 0, is it?
Yeah, 0.
So 7 minus 0, we're going to get 7. So 7 will determine how many jump that you're going to do for you to put in the value 49. Okay, so maybe I'll use a different color for this, maybe green. Okay, starting from 9, you're going to do 7 jumps. Okay, so you're going to do 7 jumps. So 1, 2, 3, 4, 5, 6, 7. So now we're going to put our 49 here. Okay. So next we got 58. So hash 58. We got 58 modulus 10, and we got 8. Again, that's a collision. And we're going to apply the second hash function, H2 of 58. And we're going to get 7 minus 58 modulus 7. What are we going to get?
Two.
58 modulus 7, is it 2? 49,
56. Yeah.
56. 49, 56, so 7 minus 2. Therefore, we get 5, right? So this one, we are going to do 5 jumps. So let me choose another color. So 5, starting from 8, we're going to do 5 jumps. So you're going to do 1, 2, 3, 4, 5. Okay, and then we're going to put our 58 here. That is how you do the double hashing. Okay, and then basically the last one is H 65, and we got 65 mod 10, and we get 5. So we put 5, 65 inside this slot. Okay, what happened? Okay, once you do the second hash function and you jump and you find that that slot is not empty, what would you do? You're going to keep doing the jump until you find an empty slot. Do you get what I mean?
So like the previous ones lah.
The previous one is you look for the next available slot. But yeah, basically you need to find, basically, you know, like in this case, rather than here, rather than this is 7, rather than you put the element inside slot number 7, you're doing 7 jumps. So if like, let's say for example, this one just now, when you do the 7 jump, did I do it properly just now, starting from 9, yeah, 7 jumps, and let's say for example here, instead of there's some elements around here. So let's say for example, when we want to put in this 49 just now, there's something else here, maybe 17 here. Let's say for example, there's 17 there. What are you going to do after the 7 jump? You are going to do another 7 more jump. 7 more times. So it's starting from here, you're going to do 1, 2, 3, 4, 5, 6, 7. That's another one. So you're going to keep until you find. So 1, 2, 3, 4, 5, 6, 7. So basically 49 is going to be here. You're going to keep jumping 7 times until you find an empty slot. Okay. So are you okay so far for in this case? Class?
So the second hash key value is just as number of times needed to jump, and that's how
Yeah.
it is.
Yeah.
Okay.
Okay. All right. So that is for the double hashing. Okay. So if you see even from here as well, you already see that how the slot is almost randomly being assigned to the key. Okay, and it will totally eliminate the clustering. But then it's just that for the double hashing, of course, you need somehow you need that additional jumping. The computation of the slot may take longer time. So, but then it will eliminate the clustering. Okay, there will be no clustering because of the randomization that it introduced. Okay, when you use the second hash function. Okay. All right. So the analysis of open hashing. So for the open addressing, we can say that at most we only have one element at most occupies each slot, and therefore our n must be lesser or equals to m, which implies that our load factor alpha is definitely less or equals to 1. Okay, and we assume that our hash function will result in uniform hashing, and basically the probe sequence we assume we basically what we wanted is that our probe sequence used to insert or search for the key is equally likely to be any permutation of 0 up until m minus 1. Okay, and basically basically we can write a theorem. Okay, so if you look at this theorem, given an open address hash table, load factor is alpha is n over m, where n is the number of elements that you want to hash, as the number of keys, and m is the size of your table, and then it is less than 1. the expected number of probe in an unsuccessful search is at most 1 over 1 minus alpha, assuming that we have a uniform hashing applied for our hash table. Okay. All right. So next lecture, we're going to be looking at another it's not advanced algorithm, it's more like advanced data structure. Okay, another advanced data structure. You know, usually last time we include this in this lecture, but then it become very rushed, so we break it down, break it into two parts. Okay, so next we're going to be looking at heaps, if I'm not mistaken. Okay, we're going to be looking at data structure called heaps. Okay, any question, class, regarding this topic? Are you good?
Yes.
Okay, so I'm not sure whether the tutorial is up, because this morning I noticed that I checked last the tutorial used to combine between lecture 7 and lecture 8. Maybe I guess try check. I'm not so sure whether the Dr. Hazrina, the coordinator, have uploaded the question. I will check with her. If you cannot find the tutorial today, check again tomorrow morning. Okay, and then let's discuss the tutorial during the question during tutorial. Okay. All right. So yeah. So I guess that's it for this week. The topic for this week. So if there's no more question, I guess I will see you during tutorial. And for group 4 and 5 next week during lecture. Right? Okay.
Just one thing, Doctor.
Yes.
If we have some questions about the project, so from where we can contact you for that?
You can always contact me via Teams.
By Teams?
Yes, you can message it through Teams. If let's say, for example, you are under my group, you can always write inside your channel and tag me, so that I'll know that you have some question, you have some question for me in regards to either your anything that relates to your group assignment. Is that all right?
Okay.
Yeah. Post it in your group channel and tag
Thank
my
you.
name, because if you don't put the tag, I wouldn't know. I would just say the highlight, because I have a lot of highlight in the word, but please tag my name. Okay.
Okay.
And then I will go and look for it.
Thank you,
Anything else? Thank you. Anything else? No? Okay then. Yes.
Sorry, if I missed it previously, but how do we determine the size of the hash table? Is it randomly chosen?
Okay, so as I mentioned before, I think in the previous slide,
I think I missed it.
how you determine the M size? Wait, let me. Where is it? Hash function deletion. Here. So when you try to do the hash function, okay. So here is how you can determine what is the size of your M.
Oh, all right, yeah. Okay, thank you.
Okay, all right.
What does it mean by a prime not too close? Like, how close is not too close? Like, what? I don't know. Is 31 a? I'm guessing like numbers like. Is 31 a bad example then, or
To the power
31 a good
of
choice? Since
25. I don't know. Maybe if let's say 24, 20. I don't know. Maybe close would be something like close. We try to
avoid power of twos, power of twos in general.
an exact power of 2. Yeah. So if let's say prime number, I don't remember the sequence of the prime number, but if you look at the sequence of the prime number, okay, and you don't want that prime number is close to the exact number to the power of 2. So if let's say for example, what is the prime number? 23. Is 23 a prime number?
Yes.
So 23 is a prime number. So it is, if let's say it is quite close to the to 25. So 25 is the power of 5 power of 2.
Mm.
So try to avoid those numbers. Not too close.
Okay.
So if I'm not mistaken, for the prime number that you use for your Rabin Cup, so, like either you use 5 or 101, right? If I'm so those are some of the what a few example of a good number of M. Okay.
Okay.
And then provided you have to look into the number of your element as well, because you want to make sure that your the size of your table is not too big for your element. And then if let's say if your input is growing, once if you check that if you let's say your table is almost starting to fill up, you need to resize your table, and you have to do a rehash of all your keys. Okay.
Okay.
Yes. No. All right. Okay. Any more questions? Good. All right. All right. So I'll see you in the next class. Thank you, everyone. Stop.
Thank you, Doctor.
Hey, doctor.
Thank you.
Thanks, Doctor.
Bye. Assalamualaikum.
Thank you,
Bye. Good
Doctor.
afternoon. Bye.
Thank you, Doctor.
Thank you, Doctor.